Howdy, and welcome to part two of chapter two, logging and all your database are belong to us. I know we baited y'all with the SQL injection database dump details, kind of like how Game of Thrones baited you with dragons. But a good story does need a proper build-up that requires details so the entire audience can see the big picture, not just a small specialized group. So today at WAF Logic with the WAF guy, we're going to be delving into the SQL injection discovery and attack queries our attacker performed to exfiltrate our database. Hence, well, the title, All Your Database Are Belong to Us. Let's just go ahead and say SQL injection is one injection you definitely do not want to take. Go ahead and ask Bobby Table's school. So today we'll be walking through the WAF logs from our awesome sauce F5 ASM WAF on the appliance and within Splunk. We'll also take a look at the SQLMap logs from our attacker, and well, hopefully this is almost as satisfying as dragons. Certainly a lot sooner. So first, we'll go ahead and extend further on the cost savings using security logs, which will lead right into our SQL database exfiltration. Now, all security products, especially WAFs, require customization to fit within your business infrastructure needs. And just like anything ever built, WAFs and security abroad require a solid foundation to be built upon, which starts with logs. They're your validation of functionality, which is one of the most critical aspects. They're checks and balances, measurements, evidence, source of truth, oracle of failure, and really so much more. The value and potential of your logs is ultimately limited to the quality in which a system can provide. Now, with that said, we'll go ahead and share our examples of some logs here. So just a second. So here we have three log examples that we'll cover, and they're the same exact event. They're just in three separate log formats to go ahead and demonstrate the difference in quality of log formats. This will extend from the log parsing portion in chapter 2, part 1, where we suggested to never use a key value log format, kind of like this one, when it comes to WAF logs, and generally for most security logs, and realistically any log if you have the ability to parse them in some manner. Now, a CSV with qualified text values, more like this one, the gold standard we had mentioned before, is definitely more ideal and efficient. And check out part 1 of chapter 2 if you missed it, and if you'd like to learn more about the key value pair versus comma separated value pair we're talking about here. But moving on, key value pairing should only be used for logs that are only ever read by a human in the raw without the ability to parse them. A common situation would be viewing logs in the command line interface, CLI, using a tail-f command, so you can kind of view it a little more real time, just because something's actively happening. Ideally, they're for one-off situations like troubleshooting, or if parsing with something such as a SIM, like Splunk, is just simply not an option. So to break this down a little bit further, here we have our gold standard log format as said before, and again, these are all the same logs, just in different formats. So this one contains 3,473 characters. Characters equates to bytes, which equates to size. Now, 128 characters out of this entire log is used for essentially the comma separated value and the text qualifiers, and that would be equivalent to these. Our bird separator value, or bird delimiter, as we mentioned before, with the quotes as the text qualifier. Now, when we look at the key value pair, we have 3,831 characters, or bytes, however you want to look at it, which is 358 characters or additional bytes extra beyond what the comma separated value log format would look like. Now, 463 of these characters are used on the key names and text qualifiers, which is 335 additional characters or bytes per log beyond just the standard 128 in the gold standard. Now, moving down further, we have just the standard format of a log that the, our ASM in our case would send, and very common for most other WAFs. And in our case, we impose the basic 2K limit. So here we have 2090 characters, but 844 of those characters are used for the key names and text qualifiers. That's a lot of wasted space. I mean, 2090 minus 844 characters, that's almost just over half of the log being useful. In other words, just slightly less than half is actually useless or garbage. Now, just for kind of a additional further point, when it comes to standard syslogging, UDP is kind of the norm, and 1K is the standard limit, and a common imposed limit on at least older style WAFs. And just taking that log, we've dropped it down to 1024K, and we can see just significantly less data from just this basic log. Now, when we're looking at the key value pair log, again, it has the same amount of data that the comma separated value has up here. However, because of the key names, you have all the additional wasted data that's unnecessary, because in our case, we have a Splunk system or a SIM system, security incident and event management, that's capable of parsing our logs and having a map to essentially identify these values in real time, saying that these are, field 7 is HTTP status request. We always know that. So we don't need to have that word in the log at every point, because again, there's size involved. And for 1 million logs times 355 additional characters, that is, well, 335 million additional bytes that you've logged. That's basically useless. So moving on. Now we'll go ahead and actually look at the individual logs and kind of break them down a little bit more. So here we have, again, the gold standard log format. Every field that's contained in here has absolute value, because as we discussed in our previous chapters, you only select the log fields in which you want that have value to you. You do not select the fields that are useless, which your standard logs tend to include quite a few of those fields that have no relevance or use to you, but they're just standard basics, get you out of the gate. So because we're WAF connoisseurs and security connoisseurs, we're going to go ahead and pick a better path and customize it. So we've done that and selected all the fields we want. So everything represented here in green is valuable in some context. Now, coming over here, we have the same gold standard log format, but with key value pairing. So this entire column is all the key value pairs, yet the data is 1-to-1 for this column here, which is the actual values, the log, the meat of the log, what matters. So by eliminating the key value pairing and just focusing on the comma separated value, that means that we're only storing this information, the important information, and cutting out all this for every log. We've already stressed enough how significant that is in cost savings, but that's the whole point of this portion. So looking at the default log format, out of the box, get you out of the gate, and be generous, give it a 64K limit. Again, I've highlighted everything that's useful in a day-to-day security-centric perspective, and everything here in green is, well, again, useful. Now, everything that is not highlighted is useless. And as you can see, as we discussed earlier, close to half of this log entry is useless to log. So it's just a ton of wasted space. So by customizing your log format and making it relative to your organization and business needs, you effectively save yourself a significant amount of money while having the highest fidelity in what you will see in your log aggregation. And so therefore, when it comes to investigations, you see a much more specific and precise set of events where actual real events happen versus just useless noise that wasn't even relevant. So we talked a lot about customizing logs to reduce the size while achieving maximum value, all while saving monetary and resource costs. That's our ultimate goal at the company, is saving money and making money. But how much does it actually cost for logging? Well, it's a great question, and unfortunately, it's a huge mystery. There's a lot of magic involved. There's sales, there's calculations, there's spreadsheets, whether you're a new customer, old customer, and how much money revenue your company makes, just the list goes on. And when it comes to on-prem versus cloud, huge difference there as well. On-prem is much more gray, cloud is much more quantifiable. There's just a lot more metrics that are used and looked at when it comes to cloud versus on-prem. Same metrics are available, they're just not looked at beyond sizing and capacity. So just because cloud is much more quantifiable and the information and estimates are publicly available to some extent, we're going to go and take a look at 3 cloud providers, AWS, Google, and Splunk, and look at their metrics. Now, we'll provide these metrics and the links inside our video description, so you can go ahead and do your own calculation, costs, and investigations, and just appease your own curiosity. But nonetheless, here we have AWS. Now, the key metric that we see here is size, gigabytes or terabytes, however you want to look at it. But that is the key metric for how AWS charges. There's other things involved, but we can see here, this is somewhat tangible and something you can make an estimate upon. Now, moving over to Google, we can see they're much more complex, just a variety of metrics and what they're looking at. But the key metric, again, is size, gigabytes, for the reference here. And they even provide an equation to figure out and estimate what your potential cost could be, which is awesome. But again, just a huge difference between the other vendor. And we'll go ahead and take a look at Splunk, and we can see again, the key metric is your data size, your log size, and the overall storage. But this one is significantly more complex. Now, for AWS and Google, those come directly from them, those metrics. When it comes to Splunk here, this is from a variety of vendors that have put together kind of like your average expectations. Just, well, they have to give you some basic numbers off the cuff when you have your initial sales, but the end contract will definitely be very different for every customer. But what we saw is very unique and different pricing models for all 3 vendors, and every other vendor out there has something similar, but just as diverse. So this is what it comes down to when I talk about saving money with effective logging, because if we're logging 100% valuable data as we presented here, then that means that we have maximum value out of what we spend in our logging. So 100% of money spent towards the actual log infrastructure and what you do is 100% used. Now, when it comes down to, say, the example for the default log format over here, just a rough estimate, we'll say 45% of the data was invaluable or garbage or just irrelevant. So that means 45% of your allocated budget and what you spend is actually, well, useless or spent on garbage or irrelevant logging. So it's just wasted space. And so that's why by effectively logging 100% valuable data, then you are saving money in the end. And this is what leads us to our dragons. So we're going to go ahead and move towards talking about the SQL database exfiltration that was done. And we'll continue to further annotate and show the value of logging effectively with 100% valuable data and the maximum data potential. So here we go. Our SecOps team just got an alert regarding a very large SQL injection attack. Very concerning. What we know so far is we've had 3,959 events, all from a single source IP address. No normal traffic from this source IP address has ever been seen before, only just this recent series of attacks. Now, the URL is for the Dibiowski Comet web app owned by the Don't Look Up app dev team. This web app failed an internal vulnerability audit 2 years ago and was removed from further vulnerability audit scanning since the application generates millions of dollars in revenue per minute. So any potential negative customer experience, especially from security-based protections designed to prevent malicious attacks, was deemed unacceptable since revenue has priority over standardized security practices. Well, now we've been called in to investigate, so let's go ahead and dig in, dive down this rabbit hole. So Naturally, as you'd expect, we have a URI for our Dibiowski Comet web app, and we're going to go and focus on that. And this is our timestamp of our event, kind of the series of when it happened. So we're going to go and look in that little window, and we're going to leverage our ASM supermassive query to go ahead and kind of dig in and see what happened. Now, as we noted in the alert, we had 3,959 total events, and sure enough, focused on just the URL, that's what we're seeing. Looks like we weren't generating millions of dollars of revenue there for a few minutes, despite what the app dev and business team says, but whatever. So we're seeing our standard fields for the events that we're looking at here. And there's our URI and there's our URI query. And then we have our types of violations and events. Now, this one doesn't look like anything too exciting, just protocol compliance failure. Nothing woohoo to get excited about that one. But let's just kind of scroll through real quick and let's just take a look at some of the, well, there you go. Okay, the second event. That's definitely SQL injection. As you can see, there's some digits and basically an AND statement, union, all, select, nulls, some script alerts, and there's an etc password call. There's a command shell, an execute command. So that's definitely not good. And then scrolling over a little bit more, we see we have quite a few signatures that have been called out. Now, we definitely have a lot more detail over here, as we had mentioned in previous videos, such as our buffer, like what the WAF has detected, which is base64 encoded, and we can decode. I'll just give you a quick example again. And there you are. I mean, that's looking pretty bad, at least in the sense that it wasn't good intentions. So kind of cruising over a little bit more, we see more base64 encoded information. And then here we actually have our decoded value because we do have some ability to decode base64 on the fly, as we had mentioned in previous videos, in part 1 for that matter. And just coming over further, we see the violation details is pretty jam-packed. And again, we've covered all this, the logging structure in a previous video in part 1. So if you want to learn more about that, check that one out. But moving forward, I mean, we have the request and the response, but right now we're just kind of getting a quick gist as to what happened. So very evident, likely we're going to see most of the events occurring in the URI and the URI query. So we'll kind of cruise through that a little bit here. And special, some more potential SQL injection right there. And just cruising on through, more SQL injection, our AND statements, obviously all encoded. So we see quite a few things going on here. Nothing too profound yet, but and more SQL injection. Considering the sheer volume, to scroll through this through the Splunk view, this is going to be very cumbersome. And again, just consistent SQL injection, multiple SQL injections, and all in the URI query thus far. So we'll go ahead and export this log set. And then once we export it, we're going to go ahead and open it up in OpenOffice Calc or Excel, depending on what you use. Since we're on a Linux platform, we will be using the OpenOffice Calc for this event. And we've already gone through and highlighted essentially the important stuff, where things actually took effect. So there were plenty of events that had occurred, but only certain ones actually resulted in the attacker getting something that had some value in the end. And out of 3,559 requests, that's a lot to go through here. So either way, that's why we highlighted it, to make this a little more simple and kind of quick and on the fly. So first, we're going to come all the way over, and what we're seeing here is everything highlighted in yellow is going to be events where, again, something was returned in the response that was of value. something that could be used, in this case, against us. So in this instance, we're going to go ahead and take this over here and copy this into our notepad just for a little more easy readability. And what we get here is this is the response. So we know all the attacks that we saw were legitimate attacks. There's something, they have intent, malicious motive. The question is, what do they get out of it? And the measurement of success is ultimately what the server responds with. Now, in this case, what we see here is the bulk of the request, nothing too special, just the HTML content. But down here is where we see some success in the SQL injection event. And we're running a standard, and equals 6495 equals 6495. That's a true statement. The classic 1 equals 1 SQL injection attack. And the end result is it does give up the name of the administrator user. Now, it could be anybody, but in this case, because it is admin, it's the first user ID account, since that's what they went for, ID:1. In this case, in very common classic style, admin was the typical first user created, hence why you'd usually go for that. So this is how they're able to discover that the user ID admin does exist. So that limits them down to what users they want to crack, and likely go for the administrator account first. Why not? Go for the gold. Now, this repeats itself through log 8, 9, and 11. Now, down here in 13, this is where things get a little more interesting. So we'll go and take this over and move it back over to our notepad and kind of look at it a little more clear. Here we've got, again, MariaDB discovery, and this is where it starts with the fatal error. And uncaught MySQL exception, blah, 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 corresponds to your MariaDB server. And this is essentially how they now know that we have a Maria database server or a MySQL server, pretty much synonymous for at least the commands in which they're going to attempt to execute to, discover future SQL injection vulnerabilities. This way they don't have to focus on potentially PostgreSQL or Microsoft SQL. They're just going to focus on the MariaDB and the MySQL database commands. Moving on further down the log, what we have is, just a variety of other discoveries that occurred. And we'll kind of take a look a little bit more in these in a second. But ultimately, where everything truly goes south is after all these other discoveries and attempts, just a variety of commands that they initiated to see, potential vulnerabilities. And a lot of them didn't really disclose anything. But finally, on attempt number 98, this is when, again, things went super south. So we'll go ahead and take this log item and dump this over into our notepad as well. And here's line item number 98. And there's actually a CV attached to this, CV 2022 for 2643. This is not relative to this very specific application. It's relative to another application, but the same vulnerability exists in multiple applications. So looking to see exactly where it all went south, again, we have our same break and fatal error, uncaught MySQL exception, and this is where it goes to say function dvwa gtid subset does not exist. And what that means is it's essentially calling out, the database itself calls out saying this is the database name and this table does not exist. GTID is a global transaction ID, and what they did is they threw a benign transaction ID, and because it doesn't exist, the SQL Server unfortunately disclosed its database name. And this allows them to further use, more focused attacks looking directly at database calls because now they know the database name. So just a more effective attack because, again, kind of like with a minute ago with the MySQL and MariaDB versus Postgres and Microsoft SQL, now they can actually focus specifically on the database name and commands that they can execute against it versus more discovery. Now, coming back over, we'll go ahead and kind of take a look and see what the actual request was that they had launched. And we can see here, again, we just copied from the get request from our log and dumped it over here for a little simplicity. And we can see the request isn't that significant. It's not very large, but let's go ahead and kind of take a look at what we were able to break out of it. So there's our violations. And here's the decoded version of that base64 value. And just a little more insight as to what it actually looked like. And one thing you can do that I was able to do is leverage this command right here, this ID, because oddly enough, it is a very consistently used transaction ID, which again is why it's benign and doesn't exist. And when you go to look it up, you find all sorts of fun things. So upon further investigation, digging through what I found online through the searches, led me to initially the source codester admission system post parameter shift SQL injection vulnerability that was discovered. And going through, there's some information in here, and just kind of digging a little bit further in, we see the CWE and a CVE mentioned. And so I kind of looked up at those. And for the CWE, Common Weakness Enumeration Site, their report is relative to some of the commands that were initially launched and, part of this whole request. And they give a very, very good explanation and breakdown. We'll have all these links included in the video description for that matter, but tons of good information here. Now, pulling up the actual CVE number that was mentioned on the initial site, CVE 222643, that leads me over to this site. And, some generic information, but we also have the references. And we see the former site that we came from, and also this GitHub. So the code repository, we go ahead and go over here and, continued student admission site, content management system, CMS, and some of the code and how it all works. And, further down the line, here we are. This is where the attack comes into play that we experienced. And there's our transaction ID. And we can see this is part of a SQLMap attack. So this is how we can kind of put together the story to say that some of this came from SQLMap or some relevance to at least these vulnerabilities. Now, further, I go ahead and take the same transaction ID and I go look up in the exploit DB, and I find this one, the Latrix 060 text access code SQL injection vulnerability. So cruising through here, again, we see the same GTID subset table call with the transaction ID that essentially doesn't exist, and error-based. So this is all the same code across the board, just multiple different applications. So what we can kind of take away from this just off the cuff right now is, despite the fact that a vulnerability may not exist for your web application, it still actually may be relative, just like we see in this case. So it has nothing to do with our application, but nonetheless, the vulnerability still exists and can be exploited in the same method. And this further gives justification on having a WAF covering all your web applications, and also having a signature set and protection plan that goes beyond just what you know about your application, because in this case, well, we didn't know. We found out the hard way. So going back to our log, we see, as said, our database name is DVWA. So we're going to go ahead and take this into our logs over here, and we're going to go hunt for that very specifically. And again, we come up immediately to our log number 98, which is where the database discovery first occurred. And as you might have guessed, I've highlighted everything in red is all the really, really bad stuff. Not just the basic discoveries, but like when something really bad happened. And everything in orange is relative to where it kind of very specifically happened at, what I'm calling out as really bad. So here in our second item, we go ahead and grab the next log item, number 99, which occurs right after the database discovery. And we'll just kind of go ahead and take a quick little look here and see what we find. And we have our fatal error again. And there's our database name and very similar error. So essentially more discovery doing very similar tactics. And we can see again, the request in itself is very, very similar. And kind of just cruising down, more discovery and more discovery. But what you're really looking for and what we're really interested in is what the end result was. So DVWA. And here is where our attacker begins to basically take the database name and all the other information they've discovered thus far and build a query to actually extract the database. And that's log item number 3932. And so with this over in Notepad, we can see, SQL injection. And we'll go ahead and take this and decode it just to make it more human readable. We like that. And again, we can definitely see SQL injection. And we can see our transaction ID from earlier. That's right there. And this is where, again, things start to really go bad because this is where we're selecting the user column and we're going for basically the column fields. And they're very specific. These are all discovered from the previous attempts that we saw, in between basically 98 and 3,932. With this, this isn't a specific vulnerability in this case. This is actually a true standard constructed SQL query. I mean, to some extent, this is where signatures are involved, but the actual CVE, there's no relative CVE in this case. I mean, this is just a standard query. Now, the end result, as we had mentioned earlier, was the database was extracted. And here we can go ahead and see the server response, and we have the response including the database commands that were requested. Not necessarily always typical, but then we see, further information about the usernames, and we can see there's some kind of a broken encoding going on here. And realistically, this broken encoding is not really encoding. It's basically a comma separator value or a field separator value. And you can see it's very consistent, AZ, BK, AD, and then you got admin, and then you got AZ, BK, AD, and then you have the encoded version of the password up to AZ, BK, AD, and essentially the user ID field, which is 1. End result, we have 4 separate users, Pablo, Gordon, all the users that we have our entire database. Now that they have all the users, well, they've got everything that they need. But why stop there? They just go a little bit further since, again, they were able to capture all the database names by leveraging these discovery events. And so that leads us to our final request. And we'll go ahead and take a look at that real quick here. And we see it's encoded. Big shocker. Let's go ahead and make it a little easier to read. And here we can go ahead and see that we have, a very similar call to what we saw earlier, union select, blah, 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 and very specific field names. And in this case, they're going for our guest book database or table. And the end result is, well, they get it. And come over here all the way to the end. And we'll copy this out. Same method. And here we see our pre-section. And there's our database commands again, pulling from the guest book. And here we go. There's our information. There's our AZBKAD field separator. and then just another separator there as well. But there you go. That is the full-fledged database exfiltration that our attacker has performed. Now, this is all from the WAF perspective. Just to go ahead and kind of give the full perspective, we've actually contacted our attacker, hacker, and we're going to go ahead and rope them in, and we're actually going to take a look at their side and see what they got out of all this as well. Well, the WAF guy caught me, and now he's called me out, and I have to explain my crimes and how WAF Logic's database are belong to us. I discovered they had the ID parameter on a damn vulnerable web application, apparently DiBiaski's comment, and it was vulnerable to SQL injection attacks. So I leveraged SQLMap, just like any attacker would consider, to go and see what I could find. And well, it was juicy and delicious. First, I constructed a request I captured using a proxy tool such as Burp Suite. And I noticed the PHP session ID did not have any expiration, so I knew I could replay this. And WAF Logic would do well to add an expiration to the PHP session ID and enforce it at the web server and possibly even their own WAF. But let's go ahead and take a look at that request here. And you can see it's a fairly standard web request, and there's our PHP session ID for the cookie. And as said, there's no expiration date. And that's how I'm able to essentially consistently use the same session ID and, well, have an active connection without any fault. Next, I take this request, and this is where I launch the SQLMap command. And in this case, I'm just doing a fairly standard discovery, nothing super exciting, but in the end, it actually is super exciting. Let's go ahead and run the command, and let's see what it looks like as we run it. And here we go for our discovery. And as what the WAF guy had advised you of, it did discover that the backend was MySQL, or MariaDB as was blatantly discovered, but as said, they were synonymous. And so we're going to go ahead and, as it requests, we'd like to skip all the other potential databases such as Postgres and Microsoft SQL and just focus on the MySQL aspect. So we'll go ahead and do that. And would we like to continue? Yes, we'll carry on. And we're running just a bunch of standard requests, discovery events for SQL injection, just to see what we'll find and kind of go from there. And wow, lo and behold, kind of as we predicted and discovered, the ID parameter is vulnerable. So would we like to keep testing this or proceed to anything else? We'll just go with the default standard and focus on the one that we do know. And let's go ahead and see what we get. Would we like to store password and hashes? We already have them cracked, so we'll skip that. And no dictionary cracking. And there we have it. Here's our administrator and the images they have for their avatars. There's our user IDs, Gordon, Lee, Pablo, Smithy. There's our passwords, which again, as was requested, we could go ahead and decode and crack later on, or essentially now. But for the sake of, show and tell, we won't go through that process. But nonetheless, yeah, this is their entire database that I've now exfiltrated. Pretty neat stuff. And then here we have additionally their guest book that I've also exfiltrated, as was demonstrated to you. So this is how simple an attack can be for just a simple discovery that can actually lead to ultimate exfiltration, and leveraging standard attacks that are quite commonly known that are for one specific system, but end up being leveraged for multiple other systems and applications, because oddly enough, developers, it's a common practice to copy and paste code from other projects just because it's a shorter path. And if it's already been created, why reinvent the wheel? So with all that said, this is essentially how I was able to exfiltrate the WAF logic database, and now all their database are belong to us. Thank you, and we'll throw it back over to the WAF guy while I call my lawyer. Well, thank you, Captain Anonymous, for coming clean with your crimes, and we'll be sure the prosecutor knows about your cooperation during sentencing here. Now, some conclusions that we do hope you get from part 1 and 2 of chapter 2 is the value of customizing your logs and how it can provide savings in a variety of ways. In our worst case database exfiltration scenario, we see the most critical log field is the server response. Now, while we identified nearly 4,000 attacks, there were only 2 that resulted in the database really being dumped. With a standard log configuration and just simply a limitation of some WAFs where response logging is not available, we would only know the attacks that occurred and not the outcome, unless, of course, we replay the attacks ourselves, and that just simply is not feasible for every attack seen on a daily basis. Now, since we did log the server response action of the dump, we now know just how serious the event was and where to properly allocate our resources for the technical, legal, regulatory, and worse, potentially public brand reputation remediation efforts we will need to make versus potentially indefinitely never even knowing the database was even exfiltrated. Now, we did discover the true identity of our attacker for that matter. It was none other than, well, the WAF guy himself. It just goes to show, though, the insider threat is real, and the zero trust model, when custom tailored to the organization's needs and goals, leveraging the right skill sets and experience is a critical methodology to follow. As said, this was a mock scenario, but using real world tools and attacks and live systems, including enterprise grade mitigation technologies and techniques for that matter. Now, no databases were harmed in the making of this chapter, and no, I don't actually have to call my lawyer. Thank God. But we do hope you enjoyed your dragons, and more so you learned something. We hope you look forward to our future WAF Life series videos as well. Our upcoming topics will cover security policy, structuring, and tuning techniques, including potential 100% reliable zero-day mitigation controls leveraging the WAF. So for now, stay safe, stay secure, and until next time, thank you and have yourself a wonderful day and enjoy the WAF life.